Hello, everybody. Welcome back to Mathematical Statistics. We are on the hunt for the UMVU, the uniformly minimum variance unbiased estimator, the greatest estimator in all the land. And last time I hinted that the UMVU was going to depend on a sufficient statistic. So you know what a statistic is already. It's any function of the data. It could be the sample mean x bar, the sample variance s squared. It could be the minimum of the data. It could be the range, the max minus the min. It could be the max minus the min divided by capital S, the square root of that sample variance. It could be really anything. And the question is, in estimation, when you want to estimate theta or some function of theta, do you really need all of the data being x1 through xn, or is it enough that you only have, or that I bring you a statistic or a group of statistics? So maybe you just are going to need the sum of the x's, or the sum of the x's individually squared, or both, or maybe the sum of the x's and the maximum, or something like that. Is that sufficient for you to estimate what you want to estimate? And that question as posed, it doesn't really make sense, because an estimator does not have to have any qualities at all. We can sort of estimate anything with anything. It would just be a bad estimator. So we do need to be a little more precise with this definition of enough or sufficient. And it has to do with conditional probability. So let me remind you, if you have x1 through xn, they could be IID, but more generally, I'm going to say with a joint PDF, f of a vector x and theta could be vector valued. It could be like a mu and a sigma squared, or an alpha and a beta, or, it could even have higher dimensions than that. So a statistic S, I've been calling my statistics T, but now since I want it to be a sufficient statistic, I'm going to call it S. This is some function of the data being the x1 through xn. And this function could be a one-dimensional function, or it could be a two-dimensional function. So just over here real quick, your statistic might be the sum of the x's, or it might be like a pair of statistics, the sum of the x's and the sum of the x's individually squared, something like that. A statistic is sufficient for estimating either theta or a function of theta. And we say this many ways, because if you have like a p parameter in a geometric distribution and a binomial distribution, the statistic you need that would be sufficient for estimating it might be different. So it also has to do with the distribution as well as the parameters. In that case, it actually would be the same statistic, but never mind. But it's sufficient, usually we might say, for the model, which is going to include everything. It's going to include the fact that you started with IID negative binomial random variables, and what you want to estimate is some complicated function of the parameters. It's sufficient if the conditional distribution of, so x1 through xn, this is going to be a joint distribution, given S, which is a random variable, is theta free. It doesn't depend on theta, which is a way of saying more formally that this information, once you have this statistic, this information here is not going to give you more information about theta. And if it's going to be theta free, it's certainly not depending on theta squared either, or it wouldn't have been theta free. So any function of theta, this is not going to depend on theta once this has been given. And so if that's the case, we call S a sufficient statistic. And last time we looked at the Bernoulli distribution, and we kind of guessed at a sufficient statistic, and we showed it was sufficient using this definition. We looked at the joint probability that capital X1 equals little x1 out through capital Xn equals little xn, given capital S equals little s, and we worked through that, and we showed that it didn't depend on the unknown parameter p in that case for the Bernoulli distribution. But something interesting happened along the way that I claim will happen every time. So although this is the definition of sufficiency, whether we have discrete or continuous random variables, it's usually easiest to talk about this conditional stuff in the discrete case where we have probability. So last time we looked at the probability that x1 equals x1 out through xn equals little xn, given s equals little s. And this is the probability. This is the big n plus one dimensional joint probability of all this stuff happening, so comma S equals S, over the probability that S equals S. So we saw something kind of interesting last time. This S is some kind of function, S of the vector of x's. And so here I've got a capital X1 through capital Xn, and this may be something like the sum as I goes from 1 to n of the x's. But the lowercase things are just things we're plugging in. And if you don't plug in things that make sense, then this whole probability is going to be 0. In fact, we get that this is equal to 0 if lowercase x does not equal this function of the lowercase x's. And if it does, then this information is redundant. We had examples last time where we talked about the probability that x1 is 3 and x2 is 4 and x1 plus x2 is 7. That's just redundant information, and you can kind of throw that out because you do have that happening, that x1 plus x2 is 7 if x1 is 3 and x2 is 4. So in that case, we dropped the s equals s part. And so that will happen every time. So this numerator is slightly simplified. If little s does equal this function of the little x's. Now, we want, in order for S to be a sufficient statistic, we want this result to be theta free. And this certainly does not depend on theta. So the question is, does this? Theta is the parameter that generated the x's. So currently, this numerator will very likely depend on theta and this denominator as well. But hopefully we can get cancellation so that entire fraction does not depend on theta. And in the end, if there's no thetas left, then the statistic is sufficient for the model or for estimating theta or any function of theta. Okay, so let's zoom in on this and also start to talk about it in the continuous setting. What you're seeing right there in that green circle is a joint PDF. So like an F of all the x's and probably theta over a marginal PDF for S, which also probably has a theta in it. And we want this to be something that is theta free. So I'm going to call this h of x. So as the notation suggests, since there's no theta there, this is just something that is theta free. So the question for sufficiency becomes, does the joint PDF for the data factor into a quote unquote pure x part with no thetas times a PDF for a sufficient statistic, which could be vector valued? Fortunately, there is an easier criterion for establishing whether or not something is sufficient, and it's known as Neyman's factorization criterion for sufficiency. So what Neyman's factorization criterion says is if you have x1 through xn with a joint PDF f of x and theta, if you can factor the joint PDF as follows. So the joint PDF, I want to be able to factor it into a pure x part, which may not even depend on x. Point is, it doesn't depend on theta. So this h of x might be a constant times. Now, before I said that we need the PDF for the sufficient statistic, but this is only a sufficient condition for us to get that conditional distribution not depending on theta. You know, we got it from this, and we got that from not wanting this to depend on theta. But Neyman says that What we're looking for is some other function, which does not have to be a PDF. And it is going to be a function of x through another function called s and theta. So this is not a PDF, and the statistic has yet to be defined. So I don't know what s of x is, but what you're looking for is pure x stuff, or at least no theta. Again, you could have like h of x equals a constant. And then you're looking for the rest of the joint PDF to be where you have x stuff and the statistic kind of mixed up. So x and theta stuff like mixed together. And what you do is you go into that function and you see how the x's appear. Do they appear in like one clump or a couple of clumps? And I realize that makes no sense at all. So let me go right to the example. Let's go back to our Bernoulli example. Suppose I have x1 through xn, IID Bernoulli with parameter p. I want to find a sufficient statistic for estimating p or for this model. Because it doesn't just depend on p, but it depends on the fact that we had a Bernoulli distribution. So it's all sort of wrapped up in this model. I am not giving you a statistic and saying show that it's sufficient. I'm saying find one in the first place. And I do say A because sufficient statistics are so far from unique. They can have, we saw last time that, if the sum of the x's is sufficient, it's enough for you to estimate the unknown parameter here, then the sum of the x's plus another statistic, throw it in as well, is also sufficient. It's more than sufficient. And having all the data, x1 through xn, is always sufficient. And having even a one-dimensional sufficient statistic like the sum of the x's for estimating p, any one-to-one function of that is definitely sufficient as well, because you can get the information about the sum of the x's back from that one-to-one function on the sum of the x's. So there are a lot of sufficient statistics, a lot. And so let's just find a sufficient statistic and keep in mind for what's coming in the future, our goal is really to bring down the dimensionality of the problem. So yes, if this was on your exam and you answered my statistic is all the x's, an n-dimensional statistic, you would always be right. But let's try to do this in good faith. Let's try to actually boil things down to one or two or maybe three statistics and not all n pieces of information. So the factorization criterion says you want to look at the joint PDF. This is, in this case, f of the vector x and p. And because these are IID, this is a product as I goes from 1 to n of the individual PDF for xi and p. Because these are Bernoulli, this is p to the xi, 1 minus p to the 1 minus xi, and then an indicator. And indicators are very important to use whenever you're doing any sort of like theorem that involves a factorization, that involves separating things. Remember, we talked about showing that random variables x and y are independent by showing that the joint PDF for x and y factors into the product of the marginals. But then we had that cheaty way of doing it where we said, I don't even need to integrate or sum to find the marginals. I just need it to factor as long as you include the indicator parts, because the x's and y's could be tangled together in there. Here we have another kind of factorization criterion, and we need to include the indicators when the goal is to separate it into the pure x stuff and then the x mixed with the parameter stuff. So definitely you want these indicators in here to use this theorem. If I multiply this out, I get p to the sum of the x's, 1 minus p to the n minus the sum of the x's, and then I get a product as I goes from 1 to n of these indicators that say that each xi comes out of this discrete set containing only two values, 0 and 1. So now we want to try to factor this into pure x stuff only. And there's only, without the parameter, and there's only one pure x piece I see here, and that's right here. So I think I'm not going to rewrite this after this one time. But here is the part that does not depend on the parameter p. This is the quote unquote pure x stuff. And this is how I'm going to define h of x. If you did not use indicators, you would miss that, and you might be okay. You're going to have trouble when the parameter's in the indicator, though. But if this circled product of indicators was not there, you could say your h of x was identically 1. The point really is the rest of it, where the x's and the p's are kind of mixed together. So this is going to be a function g. It's not necessarily a PDF, and it's going to be a function of the x's through some other function s and p. So what does that mean? It means once you separate out the pure x stuff and look at the rest of it, you go in there and you see how the x's are represented. Do you need all of the x's to evaluate that function that I just put the rectangle around? No, you just need the sum of the x's. They appear through this statistic. So when we started this example here, I didn't say show that the sum of the x's was sufficient. We just wrote down the joint PDF for the Bernoulli distribution. We factored it into a pure x part and the rest of it, and we looked at the rest of it and found how the x's appear. Do they appear in like a clump of things? Yeah, one clump, the sum of the x's. So this means that the statistic S, capital S, which is the sum of the capital XI, is sufficient. And then you would say something like by the factorization criterion or by Neyman's factorization criterion. So that is nice and fast. We not only popped out the statistic, but we didn't have to go through all that work of looking at the conditional joint PDF for x1 through xn given s. So let's do a continuous example. The factorization criterion works the same, even though we can't quite interpret the joint PDF as probability anymore. I want to do the exponential distribution. So suppose we have x1 through xn, IID, exponential with rate lambda. Let's find a sufficient statistic for estimating lambda, or for estimating a function of lambda, or more generally for this exponential model. We're going to try Neyman's factorization criterion. So we want to look at the joint PDF. This is f of the vector x and lambda. These are IID random variables, so we get it by looking at the product of one PDF over and over again with the different xi's plugged in. Oops. And for the exponential, this is the product of lambda e to the minus lambda xi and an indicator that says that xi is somewhere between 0 and infinity. Again, the indicator is important because our goal is to separate x stuff and theta stuff. And if the parameter's in the indicator, then that could cause problems. And we'll do examples. We'll see what to do in that case. But let's just multiply this out. This is lambda e to the minus lambda, the sum of the x's, and then a product, I going from 1 to n of some indicators. And now you want to look at this and you want to take all the pure x stuff out where there's no parameter. And that is right here. I won't bother reordering things. But this is the pure x stuff. And then over here is parameters and x stuff combined. So this is the g of s of x and lambda, and the s of x is representing a function that the x's are going through. So you look at this part and you say, how do the x's appear? They appear again as a sum. So by the factorization criterion, or by Neyman's factorization criterion, the statistic capital S, which is the sum of the capital X's, is sufficient for this model. Again, the beauty of this is twofold. Number one, you don't have to go through the hard work of looking at the conditional joint PDF. And number two, you don't even have to guess at a sufficient statistic for which, you would condition on. It pops it right out for you. Let's do something with 2 dimensions. How about a normal distribution? So suppose we have x1 through xn, IID, normal, mu, sigma squared, and we're going to want to estimate mu and sigma squared. And I want to know what statistics would be enough to give you so that I don't have to carry in all the data x1 through xn. Factorization criterion. The joint PDF, because these are IID, this is the product as I goes from 1 to n, 1 over the square root of 2 pi sigma squared e to the minus 1 over 2 sigma squared xi minus mu squared. And then I generally don't have an indicator for the normal distribution because it would say that xi goes from minus infinity to infinity, and that's 1 everywhere. But if you're worried, given all the warnings I just gave you, you can put that in. It will still work. So let's multiply this out. I've got 2 pi sigma squared to the 1/2 power in the denominator, so that's 2 pi sigma squared to the negative 1/2, and I have n of those. So we get 2 pi sigma squared to the minus n over 2, and then I'm going to write this down on one line. So exp of x is just a way to say e to the x, but we've got complicated superscripts and subscripts on superscripts, so it's nice to use sometimes. And I get minus 1 over 2 sigma squared, the sum xi minus mu squared. Okay, so currently I don't see any pure x stuff, but I'm not finished simplifying this. You could say it appears that h of x is identically 1 because there's no pure x stuff. You could separate this out and have 2 pi to the minus n over 2 sigma squared to the minus n over 2, and you could say that h of x is the constant in x, 2 pi to the minus n over 2, and maybe even we can get more out of this. I don't know. Let's see. But what I do want to stop you from doing is saying, okay, I'm going to take h to be one of these, and then all the rest of it is g. And how do the x's appear? They appear through this statistic. And then don't write this is wrong, but returning the statistic, the sum of the xi minus mu squared. This is wrong. And the reason is because, well, I'm assuming we don't know either parameter. A statistic has to be a function of the data. When we've looked at functions of the data and the parameters, we've built things called pivotal quantities, but those usually aren't referred to as statistics if they're functions of the unknown parameter. So if you were doing this problem and sigma squared was unknown, but mu was known, that would be okay. But this is not a statistic that you want to use to estimate the unknown parameters if it involves an unknown parameter. So let me erase that big mess. I am going to rework this PDF just a little bit. I don't want to use this as a statistic. Let's square that out and run the sum through. This is 2 pi sigma squared to the minus n over 2 e to the minus 1 over 2 sigma squared times the sum of the xi squared. And then we get minus 2 mu xi and the sum of those, And when multiplying by this, we get positive 1 over sigma squared mu sum of the xi. And then the final term here is mu squared n times, so n mu squared. So I get minus n mu squared over 2 sigma squared. So this could be factored into 3e's if you want, but it's not that helpful here. One thing you would notice is that the final term does not depend on x at all. That's not really relevant, though, for the factorization criterion. We are not trying to get a pure parameter part. We're trying to get a pure x part, and then the x's and the parameters mixed. So this is going to be part of the function where the x's and the parameters are mixed, because that's the only place where we have parameters at all. Okay, so the factorization criterion says, take h of x to be the pure x part. I'm going to take h of x to be identically 1. As mentioned, we could take it to be this part as well. And then I'm going to take all of this to be g of s of x and the parameters. And you look in there and you see how are the x's represented. I see them in two quote unquote clumps. I see the sum of the x's squared and the sum of the x's. So it appears a two-dimensional sufficient statistic is warranted here, and that's usually the case when you're talking about two parameters. We can say by so the s of x here is the sum of the x's squared and the sum of the x's. It's a vector valued statistic, and you can write that in either order. But by the factorization criterion, the statistic S, consisting of the capital sum of the x's squared and the sum of the x's, is sufficient for estimating the unknown parameters for the normal distribution. You could list these separately and not as a vector valued statistic, and you would say they're jointly sufficient, and that's fine too. So, not surprising, right? If you're going to estimate mu, I bet you're going to use x bar, which is the sum of the x's over n. So I only need the sum of the x's to write that down. And the sample variance, it's written with a, well, it's first written like this, but you can run the square out and run the sum through, and you can rewrite it like this. And this is a function of this statistic and this statistic. And so this is going to be enough if you're going to use the standard estimators for mu and sigma squared. But I'm claiming it's enough in this deeper sense of the conditional PDF of x1 through xn, once these are given and known, will not have any more information about mu or sigma squared. Okay, so let's do at least one with the parameter in the indicator. How about the good old uniform distribution on 0 to theta? So suppose I have x1 through xn, IID, uniform 0 theta. The PDF there is just the flat line with height 1 over theta, and then an indicator saying that each xi is between 0 and theta. So let's look at the joint PDF. These are IID, so we get the product, 1 over theta, and let's multiply this out. I get 1 over theta to the n, and I get a product of indicators. Now, we've seen other ways to write this product of indicators, especially when we're trying to sort of pare down information. You don't have to do this, but I'm gonna give 3 answers for this problem. So this can be written as 1 over theta to the n, and then an indicator that says that the minimum, so x1 with parentheses, is between 0 and theta, times the indicator that says the maximum is between 0 and theta. But we can also write this as 1 over theta to the n, and we can say that the minimum is between 0 and the maximum, as long as the maximum is between 0 and theta. These 3 lines are 3 equivalent ways to write the joint PDF for these IID uniform 0 theta random variables. If we look at the last line, it appears that I have some pure x stuff here without parameter, and this would be my h of x. And then the rest of it would be a function g of the data through a function s and the parameter. And if you look at that peanut shaped, that's not it. What kind of peanut looks like that? But if you look at that weird lasso thing, the x's appear in there only as a maximum. So by the factorization criterion, a sufficient statistic would be the maximum by the factorization criterion. But if you didn't massage the joint PDF all the way to that point, maybe you stopped back here. In this case, I see no pure X stuff. Every one of those terms, this, and this, involves parameters. But the data appears, I don't need all of the data to evaluate that. I need the minimum and the maximum. That is also a sufficient statistic. Remember, if the max is sufficient or enough for you to do the estimation, then this is more than enough. So it is sufficient. It's enough. It's just, not like minimally sufficient, which is something I do need to formally define eventually. But let's say you didn't even catch that factorization. If you went all the way back to this line, now I don't have any one lump or statistic I can build out of the x's that I can take to evaluate this. In order to evaluate this from the data, I need every single x. I need to put every x into that indicator and see whether the indicator is 0 or 1. So the factorization criterion here gives us that the n-dimensional statistic x1 through xn is sufficient for estimating the parameter here. And we saw last time that having the entire data set is always going to be sufficient. So we have 3 answers here. And just given what's going to come ahead, if I were you, I would look for kind of condensing the information down to as little information as possible that's needed to estimate the parameter. So the indicator, including that, was very important here. Let's just do one more. Have we done enough of these? Let's just do a quick beta distribution. How about x1 through xn, iid, beta, AB, where those are 2 unknown parameters. The joint PDF, because we have IID stuff, is the product as I goes from 1 to n of this thing called a beta function in the denominator, and then xi to the a minus 1, 1 minus xi to the b minus 1, and an indicator saying that each xi is between 0 and 1. Don't worry if you don't know the beta function. We've got 1 over this beta function to the nth power. I'm going to write this down here first. I've got a product of xi each to the a minus 1. But that can be written as the product of the xi all to the a minus 1. And for the same reason we just talked about in the last example, I want to get my x's into like a clump. I don't want to need each individual x to put them in to evaluate this. So I'm going to use this way to write down this product. This is the product as I goes from 1 to n of xi all to the a minus 1. And similarly, this becomes the product as I goes from 1 to n of 1 minus xi all to the b minus 1, and a product as I goes from 1 to n of the indicators, because your goal is to condense down the x's into statistics. Okay, by the factorization criterion, I'm looking for a pure x part, or at least no parameter, and that appears right here. This is your h of x. This is pure parameter, but again, there is no pure parameter requirement for the factorization criterion. So you want to get the stuff that does not involve the parameter. I keep saying pure x stuff, but if it's constant and doesn't involve the x's, that's okay. So by h of x, I mean no parameter. And then the rest of it, this is g of some function of the x's and the parameters. And in order to evaluate this function, instead of having the individual x's, it is enough to have this product of the x's and also this product of 1 minus the x's, which you actually can't get out of just the product of the x's. So you need both of those statistics. And the final answer is, well, here, let me write it's a vector of sufficient statistics. I'm just going to make these lowercase just to show you what this S is. But to finish this off, we'd say by the factorization criterion, the statistic S consisting of the product as I goes from 1 to n of the capital Xi and the product as I goes from 1 to n of 1 minus the capital Xi, this is sufficient for estimating A and B in this model, the beta distribution. If, for example, B was already known and we just had one unknown parameter A, then this part right here could move into part of your h of x function because it does not depend on any unknown parameters, which would only be A in that example. So if you only need to estimate A and someone already gave you B, like, like a beta A3 distribution, then you're only going to end up with this as your sufficient statistic. But yes, generally, when you have to estimate two parameters, you're going to need two statistics. Maybe more, maybe less. Sometimes things cancel out, but generally, that's what you're looking for. Okay, so boy, that's a lot of examples. I guess no one's ever complained about having too many examples, I guess, but let's get on to something else. This is how we generally find sufficient statistics quickly and verify that they're sufficient without having to go through looking at the conditional joint PDF. I want to move to something else right now that is going to also move us towards the UMVU. But before we can talk about that, I need to talk about conditional expectation and variance. So I'm going to have kind of a long list of things. I guess I'll use bullets here. If you compute the expected value of a random variable, this is going to be a sum or an integral, depending on whether that variable is discrete or continuous. And I'm just going to write things continuous here, but I could write these all with sums and make it use a discrete notation. So this is going to be an integral from minus infinity to infinity of x times a PDF for x dx. And after you do that integral and you plug in your minus infinity and infinity, you get a constant, right? You have integrated out the randomness. If you want to compute a conditional expectation, and I haven't even defined this yet, so I'm going to define it right now as part of this bullet. This is still an average for x. That's the thing you want the weighted average for. But it's weighted using the conditional PDF for x given y. So this thing is defined to be the integral or sum of just x, but now you change the PDF you're using to a conditional PDF, and then you integrate over all the x's because that's the thing you're really averaging out. And this is a function of y. It's not random. It's a constant in that sense, but it's not numeric. It's a function of y. And let's call it g of y, not to be confused with the earlier g. We can call it something else, I guess. No, I'm going to call it g. This is some function g of y. Okay, so, and by the way, if you didn't know how to compute a conditional expectation, it's the same thing you've always done, but you use the conditional PDF. So next up, what if you want to find the expected value of x given capital Y? This is defined as that function g with capital Y plugged in. And this is a random variable. So whenever I have to do something like this, I usually write this down first and I fix that Y to make it nice and concrete for easier computation. And I get some kind of function of Y. And then in the end, you really didn't have a fixed value for Y. So at the end of that, I plug capital Y into that function, g of Y. And this is a random variable. So it has a distribution. It has its own expectation. It has a variance, right? You can find the PDF for this and its mean and variance and all the other things we've been doing all along. Let's talk about finding the mean for this. Suppose you want to find the expected value of the expected value of x given y. Maybe this shouldn't be just another bullet. This is kind of important. The other things were just note that this is constant. They're all important though. Bullets are great. How would you compute this expectation? This is like a g of capital Y. So this outer expectation is with respect to the distribution for y. So this is going to be the integral over some region that might be cut off, g of lowercase y times the PDF for y. But what is g of lowercase y? It is the expected value of x given that y equals this lowercase y. And what is this conditional expectation? It is another integral or sum, and it's an average value for x, but that gets weighted by the conditional PDF for x given y. And we average over all the x's, right? So there is that expectation in there. Let's pull the fyy into the dx, right? It's constant with respect to x, so that doesn't matter. And yeah, let's just first pull it all together into one integral. And maybe we're going to change the order of integration here. But x, f, x, y, x, y, f sub y, y, d, x, dy. So this, right, this definition for this conditional PDF is the joint PDF for x and y divided by this marginal PDF. So when you multiply, you get the joint non-conditional PDF. So I don't want to try to integrate x out because there's x's over here, which make this kind of complicated. Let's flip the order of integration. I want to do dy dx. And if I'm going to do that, then I can pull this x out of the y integral. And if you integrate the joint PDF over all the y values, that gives you the marginal PDF for x. So we've got the integral minus infinity to infinity of x times the marginal PDF for x dx. And that is the expected value for x. We started with this expectation and got the expected value for x. We have shown that the expected value of the expected value of x given y is the expected value for x. This is known as the law of the iterated expectation. And you can just take this, from this point forward. If you see an expectation like this, you'll know that it reduces to something like this. You don't have to prove it again. This is going to be super useful for finding the UMVU. But I have another bullet for you, and it's about conditional variance. So suppose we talked about how to define a conditional expectation. That was back up here. Let's define conditional variance. The variance for x given y equals y, everything works the exact same way. So one way to write this would be, you know how we usually write our variance of x is the expected value of x squared minus the expected value of x all squared. You can do this, but you stay in this conditional universe where y equals y. In fact, everything still works in this conditional universe. Like expectation is still a linear operator. You can think it's really just a plain old expectation, but the PDF is a different type of PDF. And we could also write this as its kind of definition as the expected value of x minus its mean squared given y equals y. But if you do that, the mean does need to be in conditional land. So with that, let's talk about like an analog to the law of iterated expectation. It's not really an analog. So unfortunately, you cannot replace the expectations in here with variances. A variance of a conditional variance is not the original variance again. So let's talk about what it is. My final bullet today. The variance of a random variable x can be written as the variance of the expected value of x given y plus the expected value of the variance of x given y. So this is kind of important here. It's one way we can express variance if we want to bring another random variable into it. So this goes like back to basic probability where so someone is putting colored socks in drawers and they roll a die and the number on the die is the number of the drawer. And sometimes it's easier to answer a question given some information. So sometimes you care about only one event or random variable, but it's easier to answer it by dragging in another one, in this case, y. So let's prove this. To prove this, I think it's easiest to start with this. So that's what I'm going to do. The expected value of the variance of x given y. If this y was lowercase, if this was a y equals y, then the expected value is just that variance again because it's a constant. So there's nothing to take the expected value of. But this thing inside the expectation is a function of y. And one way I can write this down is here's the outside expectation. And then this is the expected value of x squared given y minus the expected value of x given y all squared. Okay, so let's run this expectation through. For the first term, you'll have an expected value of a conditional expectation. This is the law of the iterated expectation. It's going to reduce to just the expected value, the unconditional expected value of x squared. So from that first term, we get that from the law of the iterated expectation. For the second term, I'm just going to bring that expectation across and I'm just going to copy it down for the moment. How are we going to deal with this second term? Here I have inside, I have a random variable. It's a function of the capital Y. And so inside the outer expectation, I have a random variable squared. And we usually deal with the expected value of a random variable squared by unraveling the definition of variance. This is exactly what I'm going to do here, but every place there's an x, I'm going to replace every x with this entire expected value of x given y. And so let's do it. I get this expected value of x squared just sitting out here, minus the variance of the expected value of x given y. And then this minus and this plus, we're going to get another minus the expected value of the expected value of x given y all squared. We're almost there because inside the squared, law of the iterated expectation, we just get this back. So if you look at this minus, and the squared has to be down here. So this minus this is the variance. So this is the variance for x minus the variance for the expected value of x given y. Now, what did I start with? I started with this. We showed it was equal to this minus this. And so we're done. Moving things around, we've got that the variance of x is the positive variance of the expected value of x given y plus the expected value of the variance of x given y. That's what we were trying to show. We are now at the Rao-Blackwell theorem. We're still trying to get towards that UMVU. The Rao-Blackwell theorem is an awesome theorem. It's probably the best theorem you've seen in the past hour. And it takes an unbiased estimator and makes another unbiased estimator with smaller variance, which seems like a good idea when pushing towards the unbiased estimator with smallest possible variance. So let's write it out. It involves conditioning on something. And so you might see in like a journal article, someone Rao-Blackwellizing something. That usually means they're conditioning on something to lower the variance. I'm going to just state this theorem with like a bunch of bullets. So we have like an x1 through xn with a joint PDF. For us, they're usually IID. You don't need them to be IID, so I'll just say with joint probability density function or probability mass function, f of a vector x and theta. Okay, so we want to estimate theta or maybe a function of theta, so let's just do this a little more generally. We want to estimate some tau of theta, and tau of theta could just equal theta, so this will cover our bases. The setup is that we have an unbiased estimator t, which is going to be some function of the x's, for tau of theta. So i.e. the expected value of t is tau of theta. So we have some unbiased estimator. The rest of the setup is we have a sufficient statistic S, which is its own function of the data. And here is the punchline. We're going to define a statistic T star to be the expected value of T given S, right? Because I didn't say S equals little s, this is a random quantity, which itself has a distribution and expectation. And I claim a whole bunch of things. So I need a different bullet. This looks like a negative in math. I'll do like an open circle. T star is still an unbiased estimator for tau of theta. More options. Also, T star is a function of S, and that's really easy to see just by definition of this expectation, and I'll tell you why you care about that in a moment. And this is another result. The variance of T star is less than or equal to the variance for T. So you start with an unbiased estimator, and you take a sufficient statistic and you Rao-Blackwellize your unbiased estimator, and you have another unbiased estimator with potentially smaller variance, certainly not worse. And it's actually strict inequality unless T and T star are the same. That's actually a with probability 1 statement. So if you, when conditioning on S, the sufficient statistic, have a new statistic that's not the same as the statistic you started with, then you necessarily have strictly smaller variance. But sometimes it will not change. And that's kind of when you're done with the Rao-Blackwellizing. Like, because you could condition again and again, and we'll talk about that later, but let's prove this for now. And so the idea here is you want to estimate something, you have an unbiased estimator. This is a way to potentially get another unbiased estimator with smaller variance, which is one step in going towards that lowest variance unbiased estimator. We have already done all of the hard work for this proof. Let's see. Bullet point 0. T star is still unbiased for tau of theta. Let's show that. The expected value of T star was defined to be the expected value of T given S. And this is a law of iterated expectation, giving you the expected value of T. And T was an unbiased estimator for tau of theta. So we're done showing that the new T star is also an unbiased estimator for tau of theta. The second bullet point doesn't really need proving. Think of one of the very first things we talked about today. This is just going to be a function of the capital S. So it is a function of S, so we've got that one. Let's look at the variance. I am going to start not with the variance of T star, but with the variance of T. And the reason I'm going to do this is I want to use our new formula for computing variance using conditioning on things. I'm going to condition on the sufficient statistic. So this is the variance of the expected value of T given S plus the expected value of the variance of T given S. We just proved this. Come on, keep your brackets and parentheses straight. Okay. This inside is T star. Now, variance is always non-negative. So if you were to average a random variable that came from computing a variance, this is non-negative. So if I were to drop this final term, I would get something smaller. That's what I'm going to do. This whole thing is greater than or equal to the first term, which is the variance of T star. You know what? Let me make sure you see that. I'm just going to write that first term. And this is the variance of T star. So that's what we wanted to show. The variance for T star is less than or equal to the variance for T. But now let's talk about when they're actually equal and how that makes T equal to T star. Okay, so we get equality of the variances if and only if the thing I dropped was actually 0. So if and only if the expected value of the variance of T given S is equal to 0. Expectation is, you're averaging things, and the variance is always non-negative. So you can't average non-negative things and get 0 unless the things you're averaging are 0. So this happens if and only if the variance for t given s is 0, right? It's because the variance is not negative. You can certainly average positive and negative things and get a 0, but you can't average positive or non-negative things and get 0 unless they were all 0. This definition is, or one way to define this variance is the expected value of t minus the expected value of t in that conditional universe squared in that conditional universe. So all I did between this line and this line is write out the definition of that variance in one of two ways we have to compute variance. But again, this is non-negative. And how does the average of something that's non-negative be 0, even if you're averaging using a conditional PDF? This means the thing you're averaging has to be 0. So this implies that t minus the expected value of t given s squared is 0, and this implies t minus the expected value of t given s is 0. And of course, this implies that t is the expected value of t given s, and t given s was how we defined t star. So we get that they're equal. And equality of random variables is really equality with probability 1. That may not make sense right now, but I will do some examples for you where they're not exactly equal, but they're equal anytime they can actually be observed with some probability. I made that sound much worse than it is. Just hold on that for a moment, for maybe a day. Okay. Did you notice something missing in the proof? We proved all of those steps, and I never used sufficiency of the statistic S. And I don't need S to be sufficient to do any part of that proof. But if you go back up to what we're trying to show, we're trying to come up with another unbiased estimator for tau of theta. And so really we want another statistic. And a statistic is a function of the data, but not the unknown parameters. The fact that S was sufficient means that the PDF that you are integrating with respect to find this expectation, it's actually an expected value of like some function of the x's given S. And so this is dependent on the joint PDF for the x's given S. And I'm running out of time, so I'll talk about this in more detail next time. But the fact that S is sufficient, even though I didn't use it in the proof, makes this result, and therefore this, theta-free. So if you're trying to go from an estimator T to a presumably better estimator T star, it's not helpful if that T star involves the unknown parameter that you're trying to estimate. So I didn't use sufficiency in the proof, but it does ensure that this is a statistic that doesn't depend on any unknown parameters. So this sounds like it's going to be really useful. And we're going to do lots of examples next time. But I'm out of time for today. And I even hit Anvu next time. At the very latest, one more class after that. So I hope to see you next time on Mathematical Statistics.